In this series of videos I'm attempting to resurrect this HP9845 computer. As you can see, I've stripped it down, and I've stripped it down into its major sub-assemblies, and the idea is to go through each of those assemblies, check them as far as we can on the bench, and then start to reassemble the main unit. So as you can see, I've got just the chassis here. I've taken most of the parts off. The only parts I haven't taken off are the rubber feet, the clip to hold in the ribbon cable, and the two metal brackets at the front. Everything else I've taken off. I've inspected it. There's no significant damage to it. The only real damage is the paint at the front has worn through, but I'm going to leave that. It's part of the age of the machine, so I won't mess with that. And it doesn't look too bad, and if I was to start refinishing that, I'd have an issue because of course the top cover has got text on it, and that's silk screened directly onto the panel, so I'd have an issue, and if you recoat just half of it, it would look a bit odd, and it's probably better to leave the original paint on it anyway. It's part of the history of the machine. So as I say, I've looked at the chassis and it's in good condition. So the next thing is the main motherboard, and again I've cleaned this. I've inspected it under a microscope. I've had to bend some of the connections back on some of these edge connectors. Some of the tabs were bent out of the way. It's fairly common on these. The boards can get waggled about a little bit, and it can open up the contacts, and the machine can become a bit unreliable. When we've got this out, these are always interesting to look at. It will give you quite a good indication as to the general architecture of the machine. So what we've got here is this connector is the connector that goes to the front panel and all the bits and pieces on the front panel. And you can see this bus that runs all the way back to the connector that goes to the back plane, which is this one. You'll also notice these. So we've got these two connections which are for the two ROM drawers. One goes to this side and the other goes to this side, and as I said, you have two separate processors, and we'll look at their function in a future video. But also notice on this center portion you have these areas, and if you turn this over, you can see that these buses run from side to side as well as down the center of the machine. So you've got one down here that goes all the way across, and then you've got this one here that goes all the way across and also joins onto the center bus that runs down the center of the machine. So you can kind of see the way that all the different elements are interconnected. It's a fairly simple motherboard, but it is multi-layer. It's not just two-sided, so it is quite a substantial board. Very nicely made. Usual heavy gold plating that's common of HP machines of the era, and one of the reasons I think that they are so reliable. But this has come up very clean. There was a bit of corrosion around this connector, but I've cleaned that off, and that's come up nice and clean as well. Straightened the pins on it, checked everything else, and it seems to be in very good order. So I can now refit this to the chassis. I'll fit just the screws that are required at this point. There's a lot of screws on this, but a lot are screws that also hold something else in. So I'll refit this to the chassis. What you can do, if we get a fault with this, I might well take this back out and we can plug just the boards into this. We don't need to put all the metal work onto it. So you can either put the machine back together and use risers to gain access to the boards, or if you're doing a lot of work on this, you can just plug all the cards in on the motherboard while it's sitting on the bench. It makes it much easier to get to the various parts. And I'm not going to do that unless we really need to. It's not that difficult getting this apart, so I'm going to work on the assumption that as we start to assemble this, all we're going to need are riser boards, but if we need to, we can always strip it back down. So I'll get this bolted in. That's the motherboard bolted back in, and the next thing I'll fit are the drawers for the ROM cartridges. So just one of these goes each side. I'll clean them up first, get them bolted back in, and then we'll move on to the power supply and start looking at some actual repairs. So that is the main chassis motherboard refitted. Also the two ROM drawer guides are back in place. So what I'll do now is get this out of the way. We'll get the power supply onto the bench and we'll start work on that. So we'll now turn our attention to the power supply and start to do some actual testing. Before I can apply power to this, there's a few tasks I need to complete. Firstly, I need to give it a very good clean. As you can see, a lot of the heatsink vents are blocked. This can cause them to overheat and fail. All the reefer caps on the boards are cracked, so I need to replace those before I can really start applying power. And one other thing I'll be doing with this machine is, although I don't normally bother on the HP machines, I will be refitting some filters. These are found on pretty much all of this style of HP machine of this era, and they're nearly always gone. They disintegrate and fall to pieces. But on this particular machine they are quite important, because otherwise this is what happens. These get blocked, the supply overheats, and it very quickly fails. This is completely enclosed, so the only cooling it really gets is the air flowing through these, and if it's not getting that, it will overheat very rapidly. So I'll go and get this cleaned. We'll pull each of the boards out. I'll do some static testing, replace the caps, and then we can start testing this and see if it actually works. I've got no idea if this supply works, but we'll find out and take whatever actions are required to get it working. I've cleaned the power supply, blown out all the dirt and the debris. I've also spent a bit of time straightening the fins. These are very thin aluminium fins and they are very easily bent, and quite often people grab these and it bends the fins over, and it does restrict the airflow, and it also tends to catch dirt as it goes through, and it makes them block up much more quickly. To straighten them, all I do is get a pair of thin nosed pliers and then find the bent fins, slide the pliers in at an angle, gentle squeeze, and that's all it takes to straighten them out. And I'll just do that for all of the bent fins, get them all as straight as possible, and that will, as I say, increase the airflow through them. So I've done that on all the fins and they're now mostly straight. I'll do a final check before I put it back in. But the next thing to do is get the boards out and swap the reefer caps. So that's the next thing. The board's just unplugged, so I won't bore you showing that, but I will show you each of the boards, and then we'll start going through how to test these and carry out any repairs that we need to. So that's the next step, but before I apply power, it's out with these old reefer caps. I've unplugged all the boards from the main power supply motherboard, and I've been checking for any physical damage. You can see now the reefer caps need replacing. There's one here, one over here, one here, and there's also one on the other board. So they all need replacing before I apply any power. And I'm also testing the main smoothing caps individually. So I've taken the first one out, you can see it in the background there. That's connected to the bench supply. And in essence I'll leave them running for a while, and then I will apply an alternating load. And the reason for doing that is I want to test them under ripple current conditions, not just static. So I want to give these a thorough testing. They're 200 volt 1800 microfarads, so they are quite difficult caps to get hold of and they're expensive, so they should be okay. Never had one of these fail. But some other caps I'll be checking on here as well. A couple look a bit suspect, so I'll be checking those. Make sure all the screws and nuts that hold the power devices in place are tight, and then I'll use a multimeter, go around and check all the main devices as much as I can while they're fitted to the board. I'll check all the windings on the transformers. Luckily they pretty much all unplug, so we can just unplug the transformer windings and they'll be open circuit, so we can test them fairly easily. And I can then have a fair degree of confidence that it's safe to start applying power. Doesn't mean it's going to work, but at least we can hopefully avoid any major catastrophes. And then it's just working our way through, checking each of the rails, loading them up, make sure they behave the way they're supposed to. And I need to spend quite a lot of time doing this. As I said in the previous video, it's well worth spending time at this stage, because if we do have an issue with the supply, it can quite easily destroy some irreplaceable parts. So each of the main caps will get 24 hours on load before we refit them, and all the smaller caps I'll just do a leakage test on them. The very small caps, of course, I won't bother with. It's just really the electrolytics we're talking about here. Power devices should be reasonably easy to test in circuits. You can normally get a good indication as to whether they're good or not, and then we can start looking through the power supply. It's a very interesting supply, the way this works, and as I say, we'll look at this in a bit more detail once we can start applying power. But we can also test each of these in turn to a certain extent, and we don't need to do a all or nothing test. We can start building it back up and seeing how it behaves. So that's it for now. I'll come back once all the major testing is, or the testing of the major parts is done. Just be a few minutes for you, or a few seconds, but probably take me maybe a day and a half to complete. I've been through all the boards and used the multimeter to test all the power devices. I've taken out all the larger caps and tested those. I've had them on a power supply, testing for DC leakage and also ripple current. So they all tested fine, didn't find any faults with those at all. There's one area of the board I'm a bit concerned about, and we'll come back to that later. But haven't found any faults with the power devices. They all seem to test fine. Doesn't mean they're working, of course, but hopefully it does mean we won't get any magic smoke escaping when we start applying power. I have swapped some of the reefer caps, and they are all split, and some had actually started to fail. So the smaller ones I've swapped. The two larger ones I've removed. There's one here and one on the other board, but I haven't fitted the replacements yet. I'll fit those later, but again, these had started to fail, and in fact one of them was on the point of exploding, and these do make a mess, this size reefer cap, when they go off. So this was probably only a few minutes from failing, and so it was as well that we removed them. So that's those out of the way. It means we can now start to apply power to the boards. And as I say, I've been through them all, done as much static testing as I can. And before we start, I just want to briefly explain how this power supply works. It's quite an interesting supply, and if you're not familiar with these, then you might find this interesting. If you are familiar, you might want to skip this part. I would also say there's more than one version of the supply in these machines, so make sure you're dealing with the right version if you're following along with these videos. The main difference is in the regulator board. The other boards are actually interchangeable, but as I say, I'll come back to how this works as we start doing more in-depth testing, but for now I'll just do a very brief overview of how this system works. So if we start with the motherboard, that's this board with the two large caps, then hopefully you can see this. The schematics I have are not particularly clear. I have enhanced them, but even so it was quite difficult printing them off. But hopefully you can see enough to allow the explanation to make sense. But what we have is the mains coming into the motherboard at this point, and that's this connector, and the system can be run at either 120 volts or 240, and the only real difference is the way power is applied to this four-way connector. If it's 240 volts, the mains is effectively wired in series through here, and if it's 120, it's wired as two 120 volt supplies. But effectively from that point onwards, everything is identical. The voltages on the system are the same. So what we have is the mains coming in. It goes through a large resistor, which is this resistor here, 10 ohm 20 watt resistor, and then it goes through a bridge rectifier, which is this collection of diodes here. We'll come back to this device in a minute. So through a bridge rectifier and then onto these two large capacitors, and they are 200 volt 1800 microfarads, which might seem quite a low value. This is the main bulk storage for this entire supply, and this is a very high energy output supply. I think the 5 volt rail can put out something like 30 amps, so very high output supply. And the reason it can get away with such small capacitance as its bulk smoothing is because this doesn't use the 50 or 60 hertz mains supply to step down the voltages. This actually generates these two rails, basically plus or minus about 160 volt rail, and it uses that DC supply and it feeds it into a chopper, and then that chopper runs at about 250 kilohertz. So the entire system is transferring energy through it around 250 kilohertz, which means that it can use very small smoothing and decoupling caps. We don't need massive caps like we saw, for example, in the MDS system. And that has some major advantages, which we'll come to in a couple of minutes. So we have the plus or minus rail, so it's plus or minus 160 volts DC, and we also have this secondary supply down here, and that's formed using this transformer. And so that's this transformer. It just feeds into a few bridge rectifiers. They're the small bridge rectifiers, you probably can't see them, they're down here. And these supplies are used internally for the circuits of the supply. They don't actually supply power to the actual machine, they're just to power the power supply. And the reason it needs to do this is because it's a pulse width modulated inductively coupled switching supply. It's not a switch mode supply, it's a pulse width modulated supply. And so until the supply is running, there aren't any output rails, so we can't use the output rails to power the supply itself because they aren't present until the supply is up and running. We then have some control electronics down here. This doesn't start up until the supply is running. Actually, it's actually powered from some of the outputs of the supply, and as I've just said, they aren't present until the system is running. And then we have these latches up here, and these are again protection, which we'll come back to in a few minutes. So power comes in, charges up these caps, and we have a plus or minus DC supply. This circuit up here is a soft start, and that uses this device, and effectively what happens is the big resistor limits the inrush current when we apply power, and then when the supply starts to come to life, this device switches on and it bypasses the resistor, so that then allows it to supply full power efficiently, but it gives a nice soft start and no huge inrush current. So we've got our high voltage DC supply. That is then fed into a chopper circuit, which is, if I can find it, is this circuit. And there are two circuits here, they're identical, but we'll look at just one. And this is fed with two clocks, alternating clocks, and they basically drive the chopper, the output chopper devices. That's the power devices on this board, and it alternates the current through a secondary transformer. So this point and this point are the output of the chopper, and they feed into one of these circuits, and they feed into this point. So that's the input to another transformer. So this particular board is this one. So we've got the transformer, rectifier, and then a few capacitors. So that's all that's on these boards really. And because this is inductively coupled, it means there's no direct DC path between the input and the output. Somebody asked if there's any crowbar protection on this power supply, and the answer is no, it doesn't actually need it. There are a couple of crowbars on the lower voltage supplies, but that's just because they are low energy supplies, and if something happens on these, it's not really enough to shut down the entire supply, so they put separate crowbar protection. But the main rails don't need it because there is no direct DC path between the input and the output. And in fact, if you look at the boards, you'll see that there are very distinct separation gaps in, for example, if we look at the regulator board, down the center of it we've got this isolation gap, because we've got effectively mains on one side and our output DC supplies on the other side. Now this has a secondary advantage. Because we're running at high frequency, it means that we can have small decoupling and smoothing caps. So at any instant in time there's very little excess energy in the power supply, so if something goes wrong, in theory it should shut down fairly quickly without too much damage. In contrast to something like the MDS supplies that we looked at in the previous series, they had huge transformers, huge capacitors, and if you short those out you'll get several thousand amps for a few milliseconds, whereas this supply will die very quickly. And because it's a dynamic supply, it will also shut down and it will stop providing energy through the transformers, and it will stop the thing running. So looking back at the chopper circuit, the output of the chopper circuit is also fed through another transformer, and this is a current sensing transformer, and they are used to feed signals back to the motherboard, and in this case it's connected to this point. And as I said, there are two identical chopper circuits. There are two of these. These latches are set when the power supply is first switched on, and it effectively enables the choppers. We have this OC1, not OC1 and OC2, and they are used to control the chopper circuit. So if we look here, we have OC1, down here we have OC2, and these enable or disable the chopping circuits. So the latches that we just looked at enable these circuits, and if we get an overcurrent event because the current through this transformer is too high, then it causes the latches to reset, and that will then shut down the chopping circuits. That's the overcurrent protection for the system. And we have similar overvoltage for all the rails. As said before, it's a fairly pessimistic supply, but it does mean, in theory at least, it protects the machine from damage if we get a fault somewhere. So the second chopping circuit works in an identical way. It supplies power through to the second of our output boards. So in this case, that's this board, and this supplies some more rails. So in this case, this gives us the main plus 5 volt rail. This is the plus 5. There are two 5 volt rails on here. One's plus 5 and one's plus 5p. The plus 5p is the power supply 5 volt rail that we'll come back to in a minute. So it's important not to get them mixed up because they are completely different rails. So we've got the main 5 volts out. We've got plus or minus 18 volts. We've got the plus 12 volts, and we've got minus 12 volts, and we have plus 7 volts. So again, inductively coupled. We don't need crowbar protection on the 5 volt rail because there is no direct DC path, and if something goes wrong, we get an overcurrent or overvoltage, the chopping circuit is shut down and energy very quickly dissipates because the main smoothing caps are quite small. It's only 5600 microfarads, so quite a small cap, and the two circuits work in a pretty much identical manner. So quite a nice system. Actually quite simple. It looks complicated, but it's actually quite simple in the way that it works. Where it starts to get a bit more complicated are in the protection circuits and in the startup. So if we look now at the regulator board, so that's this board. When we first power up the power supply, the regulator board powers up, and this device is fed with raw DC power, and that comes from the motherboard. So if we go back and look at this schematic for the motherboard, that's this rail here, and that's the one that's supplied through the secondary transformer on the motherboard, and that's not switching or anything, it's just a standard transformer, rectifier and regulator supplies. So these are kind of low power supplies that are in theory always there, unless of course there's a fault in the transformer, rectifiers or regulators. But this goes through to the regulator board. This device here is this large device on the regulator, and this circuit is used as the startup control. So we firstly get this startup signal, and this is the signal that's responsible for setting various things, including these latches, and in theory puts the device into its start mode. And this also generates this 5 volt pitch, 5 volt regulator. It generates a 5 volt internal supply for the power supply. That's used to control these devices. One's a start pulse or start level indicator, and the other one is this line, and this goes through to control the pulse width modulation control circuit. And what this is for, it gives us a soft start to the pulse width modulation. So when this voltage is low, the pulse width modulation is kind of limited, and as this line starts to rise, the pulse width modulation is allowed to increase. This is of course driving the chopper board, and as the pulse width modulation increases, at some point it will intercept the loop control, where it's then put into the feedback control mode, and the pulse width modulation is then controlled through the feedback loop to control the output of the supply. And this goes through to our chopper board. So as well as the 2 chopper circuits, the tail of the chopper circuits comes through this circuit here, and this is used to control the duty cycle of the choppers. So we have the 2 clocks that are controlling the pulse duration, and then the duty cycle is controlled from this. And if we look down here, this is the PROC line, and that is the output from the pulse width modulation control. We have a clock that generates the clock signal, and we then get the it's called here a grey code counter, but it just generates the 2 out of phase clock signals. These are used to feed through to the choppers. So we've got clock 1 and clock 2. That goes through to here. So we've got clock 1, clock 2. Generates the chopping signal, and then we have the feedback loop that's used. It monitors the voltage of the output of the supply. That's fed back into our 5 volt regulator circuit, which is this. It's optically coupled, so we maintain the isolation between the mains input side and the DC out. And this is used to control the duty cycle and the pulse width modulation of the choppers. So it's closed loop, and it's, in theory, if it all works, then it maintains a very consistent output. This circuit down here is a power on reset circuit. It's fed from the main plus 5 volt output. So when the main plus 5 volt output comes up, this circuit starts timing. It's just a really simple timer circuit, and it holds the entire system, the machine, in reset for a short time. Then it releases it, and in theory the machine should then start up. So as you can see, it looks like a complex supply, but in reality it's relatively straightforward. And so we'll go back through this as we look into the supply and test it further. But we can test this in stages. We don't need to plug everything together to start with. And we'll start with the motherboard. We'll make sure we have our low voltage internal supplies, and we'll also make sure we have the B plus and B minus supply. We'll test the soft start, and we'll test the latches and make sure this all works the way it should before we plug anything else in. Okay, I've carried out as many checks as I can, and it's now time to apply power to this. I haven't tried powering this up yet, so I'm not quite sure what's going to happen. Before I power it up, just a word of caution, a trap for young players, as Dave Jones would say. If we look back at the schematic, then we have the mains coming in through the bridge rectifier to charge up these two very large caps, and we've got well over 300 volts across the caps. Not each one, it's about 160, 170 volts across each one, but they're in series, so from one to the other, B plus to B minus, we're getting about 330 volts and DC, and that's easily enough to ruin your entire day. Now for safety, there are a couple of resistors. There's a resistor across each one, a 68k resistor, and that's the ones you can't see, but they're down between the two caps. Their function is to discharge the two caps when you turn power off if there's nothing else loading them up, because up to the moment there's nothing plugged in, so these B plus, B minus don't go anywhere. So part of the testing I did with the multimeter was to test those two resistors, and they were both open circuit, so had I not replaced them, then apply power, when I powered off, these would stay charged up for a very long time. 68k resistor, still going to take a few minutes for them to discharge, but at least they will discharge, whereas without the resistors they'll stay charged up for a couple of hours, and at 300 volts, as I say, that can ruin your entire day. So I've replaced those. It's always worth checking them before you start testing, and without further ado, we'll get this plugged into the bench transformer, power it up and see what happens. So as you can see, I've attached some leads to this so we can actually connect it to the transformer. I'm in the UK, so I'm using it on the 240 volt configuration, and we'll get the multimeter in. And I'm going to bring up the voltage in stages. I don't know quite what's going to happen yet. As I say, I haven't tried powering this up yet. We'll switch this on and see what happens. And the voltage we should see should be half of our supply voltage multiplied by 1.4. So it sounds a bit odd, but it's just a rule of thumb for converting from AC, RMS AC to DC when you full wave rectify and smooth it. So it's looking good so far. I'm at about 70 volts input. I'm going to turn the power off and make sure it doesn't discharge very quickly. It should come down fairly steadily as it discharges through those resistors. But if it plummets, then we know that's something drawing a lot of current, and we shouldn't go any further until we find out what it is. But it looks fine so far, so we'll keep going up. We'll go up to 100 volts input. So nice and steady. I'm listening for any strange noises, checking for any unusual odours, and there's nothing so far. So it's past those tests. We'll go up to 150 volts. They're both the same, which is good. Up to 200 volts. And all the way up to 240. And now we'll turn the power off and see if it goes down nice and steadily, which it is doing. So that's a good sign. There's nothing drawing a lot of power from this, so it looks like there's nothing in serious need of attention. If there's anything that was pulling this down quickly, it would be getting hot. Okay, so that looks very promising indeed, so nothing untoward as yet. The next thing I want to do is check the low voltage supplies. So that's the power supply supplies. because without these we won't get any of the circuits in the supply itself coming to life. So I now need to check these three supplies. So the first one I want to check is the raw supply that goes through to the voltage regulator board. That's this one. There are test points for most of these, and the one we're interested in is this one, and we need a ground, so we'll use this ground, power this back up, and we're looking for about 8 volts on this particular rail. So 7.8, good enough. I'm going to reduce the voltage slightly going in just to make it slightly safer. It's not going to have much bearing, but just bear in mind now that we're running this about 215 volts. Okay, that's good. And now I'll check the other two voltages, the other two voltage rails, and I'm also going to check the output of these. Now they should, at the moment, be in the off state because this is supplied from the regulator board and it's not plugged in, so these shouldn't be enabled. So I'll just quickly check that. Okay, the two rails are, or the other two rails are fine, so that's all three of these rails are fine. The plus 5 volt P rail is not present, of course, because that's generated on the regulator board, and the flip-flops are in the inactive state, which they should be because we don't have the start signal. So the next thing I'm going to do is flip this back over, and we'll plug in the regulator board and see if we get the plus 5 volt P, and we can also then check to see if we're getting the clock signals and also if we're getting the startup, because as I mentioned earlier, if I find the correct schematic, this is the regulator board, and what we're looking for here is this circuit is the one we'll check first. We'll check that the incoming voltage, this is the rail we've just checked, we should get 5 volts on the output of that regulator, and that will give us our 5 volt for the power supply. And we can also check the two startup control voltages. We can then go on, if that's fine, and check the clock generator and the clock output. So we'll get the board plugged in, test these and see what we get. Okay, I've waited for the capacitors to fully discharge, and the next thing we're going to do is plug this in. So we want to see if we're getting 5 volts out, and we'll also then check to see if the clock generator is working. So this just plugs into this location. The post is for a screw that comes through from the other side, that goes through the metal panel, through the board, and holds the boards in, stops them dropping out. So we'll plug this in. As I said, I've checked the capacitors are discharged, get that plugged in, and then the next thing we want to do is see if we're getting 5 volts on this particular device. So we'll get the multimeter back in, power up the board, and again it's the first time this has been powered up, so fingers crossed we're not going to release any magic smoke. Just keeping my finger near the on-off switch just in case. Current's about 20 milliamps on the mains in, so that looks fine. And now let's check to see if we're getting any power output from this particular device. Try and do this without blocking the... So that's our input voltage. And we're getting almost exactly 5 volts out, which is good. That's the 5 volt P. I'll get the scope powered up, and we'll see if there's any clock signal on here. I've got the scope hooked up. I've actually connected the ground of the scope to ground on the power supply through a resistor. That's just to protect the scope if something goes wrong with the supply. Don't want to blow my scope up. And what we're looking at now is whether we're getting any clock output. So if we don't get any clock output, I'll track back and we'll check the oscillator. But we'll check here first. That's the easiest thing to start with. So we'll power the board up and we should see somewhere around 260 kilohertz or so coming out of this device, and that's this IC down here. And we'll check for a clock signal. And so both clocks are present. They're out of phase. They look the same, but they are out of phase. If we scope them both together, we should have two out of phase clock signals, but as you can see, they are running fine. Nice and consistent. Actually up nearly 290 kilohertz, a bit higher than I was expecting, but it's not a crystal controlled oscillator, so it will vary. But it's nice and steady. This video is getting a bit on the long side, so I'll stop it here, and in the next video in this series we'll carry on building up the supply, testing the various parts, and hopefully get the entire thing up and running.